Hello everyone, this is Abhishek Mahanti and you are watching Padak Vigyan. So students, in this video, I'll solve this question from the chapter Electric Potential. So let's get started. The question is, a hollow uncharged sphere has inner radius A and outer radius B. A point charge plus Q is placed at the center of the sphere. Find the potential Vr everywhere assuming that V equal to 0 at R equal to infinity. So it is given that we have a hollow uncharged sphere whose inner radius is A and the outer radius is B. So hollow uncharged sphere means this region is not empty, rather we have some material in this region. We have a metallic material in this region and the inner radius is A, the outer radius is B. And we have placed a positive point charge plus Q at the center of the sphere. Now we have to find the potential everywhere assuming that V is equal to 0 at R equal to infinity. So everywhere means we have to find the potential at these 4 points. The first one is outside the sphere. It means we will choose a point somewhere here which lies outside the sphere. So we have to find the potential at this point. Then we have to find the potential on the surface of the sphere. Suppose the point lies on the surface of the sphere, then what is the potential at this point? Then we have to find the potential inside the conducting material. Inside the conducting material means in between the inner sphere and the outer sphere, somewhere here. And finally we have to find the potential in the cavity. Suppose we choose a point here. At this point we have to find potential. So at these 4 different locations we have to find the electric potential. So students, to solve this question you should have this knowledge, the potential due to a charged cell. So remember that if we have a charged cell having radius capital R and if we are finding the potential at a point outside the charged cell, then V outside is equal to K Q by small r, where small r is the distance of the point from the center of the cell. So this formula will be used when the point lies outside the shell. And if we are finding the potential on the surface of the cell, then the potential on the surface, V surface, will be equal to K Q by capital R, where capital R is the radius of the cell. And if we are finding the potential inside the cell, then remember that the potential inside the cell is same as the potential on the surface of the cell. And here we have written that the potential on the surface of the cell is Kq by the capital R. So similarly V inside will also be Kq by capital R. So using these 3 important points we will write the expression for potential at different locations. So first we will find the potential. First we will find the potential outside the sphere. Potential outside the sphere. Outside the sphere means R is greater than B. Suppose a point lies somewhere here. The point P lies outside the sphere, and suppose the distance of the point P from the center of the sphere is R, then this R is definitely greater than the outer radius B of the sphere. So that's why I have written that R is greater than B. So students, just look at this diagram here. When you place a positive point charge plus Q at the center of this sphere, then what will happen? Due to electrostatic induction, minus Q amount of charge will be induced on the inner surface of the sphere and plus Q amount of charge will be induced on the outer surface. So here we have 3 types of charge configuration. The first one is a point charge plus Q. The second one is a negative charge minus Q distributed over the inner surface, and the third one is the positive charge plus Q distributed over the outer surface of the sphere. So if we are going to find the potential at P, electric potential at P, electric potential at P, then Vp is equal to the sum of potential due to the point charge, potential due to the point charge plus potential due to the inner surface, potential due to the inner surface plus potential due to the outer surface, potential due to the outer surface. Since we have three charge distributions, one point charge and two spherical charge distribution, then we have to find the potential due to all these charge distribution, and then we have to add them algebraically. So first I have to write the expression for potential due to the point charge. So we know that the point P is at a distance r from the point charge plus q. So the potential at P due to the point charge will be k q by r. Then we have to write the potential due to the inner surface. So the inner surface has a charge minus q due to electrostatic induction, and the point P lies outside the inner shell. It means the potential at the point P due to the inner shell will be k into minus q divided by r. Then I have to write the expression for the potential due to the outer surface. Again, the point P lies outside the outer surface, and the distance of the point P from the center of the outer surface is equal to how much? It is equal to r. So I can write k q by r. So we got the three expressions: potential due to the positive point charge, potential due to the inner shell, and the potential due to the outer shell. So these two terms will cancel and you will get k q by r. The potential at the point P is equal to k q by r. So I can write that V outside is equal to k q by r. Is that clear? Now we will find the potential on the sphere. The next one is potential on the sphere. Potential on the sphere. So if the point P lies on the sphere somewhere here, then the distance of the point P from the center will be equal to b. So I can write that r is equal to b. So if the potential at outside point is k q by r, then in order to write the potential on the surface of the sphere, I can write that V surface is equal to k q by b. Simply replace this r with b, so you will get the expression for V surface. Is that clear? Now we will find the potential in between the inner and the outer shell, means inside this conducting material. So the third position is what? The potential in the conducting material, potential in the conducting material means in between the inner and outer shell, the inner and outer surface, inner and outer surface. So if the point P lies somewhere here, then if the distance of the point from the center is r, then this r will be less or equal to b, and more or equal to a. So I can write that A less than or equal to R less than equal to B. So again, if you choose a point P somewhere here in between the inner and the outer surface, then you can see that this point P lies inside this positively charged cell but outside the negatively charged cell. So let us find the potential at the point P due to the 3 charge configuration. So I can write that V inside or V in is equal to, again it is the sum of potential due to the point charge, potential due to the point charge plus potential due to the inner surface or inner shell plus potential due to the outer shell, potential due to the outer shell or outer surface. So the point P is at a distance r from the point charge plus q. So the potential due to the point charge will be how much? It will be k q by r, and again the point P is outside the inner surface. You can see that the point P is outside the inner surface. So I can write that the potential due to the inner surface will be k into minus q divided by r, but the point P is inside the outer surface. You can see that the point P is inside the outer surface. So we know that the potential due to a cell at a point inside it is same as the potential on the cell. So I can write that k q by b, because the potential, because the radius of the outer surface is b, so I can write k q by b. So these two terms will cancel, you will get k q by b. So just look at this expression, V surface is equal to KQ by B, and V inside is also KQ by B. V inside means the potential in this conducting material in this region. In this region, the potential will be the same. So if you are choosing the point here or the point here, at any place inside this conducting volume, you will get the same potential, because we already know that a conductor is an equipotential surface. So the potential at every point inside this conducting volume will be same. So when you are moving from the surface of the outer cell to the surface of the inner cell, throughout this region the potential remains the same. Is that clear? Now finally we have to find the potential in the cavity. Let us find the potential in the cavity. Potential in the cavity. So potential in the cavity means, suppose I will choose a point somewhere here, the point P is inside the cavity, then I can write that R is less than A. Okay, and you can see that this point lies inside the outer surface as well as inside the inner surface. So again the potential in the cavity, V cavity, is equal to the potential due to the point charge, potential due to the point charge plus potential due to the inner surface plus potential due to the outer surface, potential due to the outer surface. Is that clear? So Again, the point P is at a distance r from the center or from the point charge plus q. So the potential due to the point charge at that point P will be k q by r, and the point P lies inside the inner shell. So the potential due to the inner surface will be k into minus q divided by a, where a is the radius of the inner surface. And again, the point P also lies inside the outer surface. So the potential at P due to the outer surface will be k q by b. So if you want to take k q common, then you will get 1 by r plus 1 by b minus 1 by a. So this is the expression for the potential in the cavity of this hollow sphere. So students, in this way you can write the expressions for the potential at every point outside the sphere, on the surface of the sphere, in the conducting volume of the sphere, and inside the cavity. Hopefully you have understood all these derivations, the concept behind it. And again, if you have any doubt, you can ask me in the comment section. So we'll meet in the next class again. Till then, have a nice day and bye bye.